organizers, for inviting me. So this is joint work with Moore and Feldman. So I want to talk about the secretary problem, and more particular about the submodular version of it. Maybe to be specific, I care about the matroid secretary problem. So that's not in the title, but I will explain to you soon what this means. Let's start slowly with the most classic version of the secretary problem. So you're given a set of n secretaries, and each one, so like the different ways to explain it. So I think of each one having a weight, a non-negative weight, and you want to hire one of them with a weight as high as possible. So the mechanics are the following. They will appear, so the weights are assigned at the beginning, but you don't know them. They appear in random order and declare their weight. So the first secretary may be a third one and says, I have a weight of 9. And now it's your choice. You can either hire that secretary or not hire the secretary. And that decision is immediate, so you have to take it now, and it's irrevocable. So if you, of course, if you hire the secretary, you're done because you hire a single one. If you don't hire that secretary, you cannot hire the secretary at a later point in time. So it's an irrevocable decision. So let's do a kind of a test run of that, of a potential algorithm. So you could reject the first secretary, move on, reject that one. You keep going, you hope for a better one. At some point, you realize that maybe you will never see a 14 again. So you hire the one with 11, for example. So here you would have an objective value of 11. And so in the original form, people cared about whether, so about trying to hire the one of highest weight. And so getting like a constant probability to hire the one of highest weight. This is not so hard to get if you think about it. What you can do is you can just observe half of the secretaries without hiring anyone. And then in the second half, you take the first one that's better than the best one you saw so far. So if you do that, then you will always succeed if the second best one is in the first half and the best one is in the second half. So you have a success probability of a quarter. And you can actually push that to 1 over en, which is the asymptotically optimal value for that problem. So if there are any questions at any time, just don't hesitate to interrupt me. I'm happy to clarify things as soon as it's still easy to clarify. So now I'm interested in the so-called matroid secretary problem. So people got more interested in the problem later because the problem is very old, actually. It's a stopping time problem, right? You see kind of weights being revealed, and you have to decide when to stop. And there's a random component, is the random arrival order. So then people got interested in more general versions of that because there are connections to mechanism design. So in particular, in versions where you can hire more than one secretary. So now I will kind of use equivalently the word secretary as I say, elements, and sometimes now in the shown example, where we'll talk about clients just to highlight this mechanism design connection, but it's all the same. So pick your favorite notion, and that will be fine. So the matroid secretary problem, there you're given a matroid on the ground set as well. And you can hire secretaries, more than one potentially, but they should be independent in the given matroid. That's the condition. So we have to be somewhat specific how precise I'll give you that matroid. Let me come back to that later. Let's just first look at an example. So I guess people here anyway know what a matroid is, so let me not define it. If you happen not to know what a matroid is, then I will give you an example. Just always think about that example, and that will be fine. So assume that you have your network operator. There's a bunch of clients. Again, clients equal to secretaries. And they want to be connected to the server. And so if a network can see capacities on the edges, and connecting a client to server is nothing else than just creating a unit path, just a path from the client to the server. So this would be one way to connect that client. And so you could, for example, also connect the client over here using this path, this path here. Okay, just move on. Sorry, this I shouldn't do. There's a capacity of 1, but I can do that, for example. Okay, let's fix that again. Okay, so this is fine. I use an edge twice, but I have a capacity of 2, so that is okay. So there would be a way to connect two of those clients. Now the game is the same. So what I can do is I want to connect a subset of clients that are connectable and of weight as high as possible. And the mechanics are the same as in the secretary problem. So a random client will appear. They all have weights. I don't know those weights. Some client will appear, will announce its weights. Let's say 4. And I can now accept or reject. Let's say I accept. So this means it has to be connectable somehow. It doesn't really matter how I connect the client for the time being. It just has to be. I have to be on the. I have to be able to connect the client. Then maybe next client appears with a weight of 7. I can connect that one as well. I do need to reroute the first one, but that's legal here. Maybe next one comes. Maybe I don't want to connect. I could connect that one, but maybe I don't want to do that because I hope that there will be higher weight further to the right. So let's just reject this client. So the number 5 in yellow, this one I cannot connect because there's there's a cut here, you see, that contains 4 clients. I already accepted 2 of them, but the cat values, if you look at the edges crossing the cut, have a total capacity of 2. So I cannot connect more than 2 clients. I already accepted 2, so I have to reject that client. I could accept the green one. I have to reject the light blue one for the same reasons I rejected the yellow one. This one I can also not accept, and this one I can connect. Now I'm done. So the total weight I gathered with that procedure is connected the brown one, the green one, the red one, and the blue one, which is 21. Right? So the outcome of my algorithm would have a value of 21. So again, the rewiring is fine because clients really just care about whether they're connected or not. They don't really care how I connect them to the server. So the constraint is so-called gamoid, the subset of clients you can connect. It's a well-known matroid. So what I will assume is that, now we want to be specific about how the problem is given. So we'll assume that the matroid is given by a so-called independence oracle that you can only apply in what you've seen so far. So you don't, it's actually a much nicer setting I explained here. Like if the full graph, the matroid is clear up front, you know where the clients are. So the problem I consider is more abstract, is more general. So you will just see a client, and you can look at all the clients that appeared so far and call the independence oracle on those clients you saw so far. You don't know where future clients appear. However, so the weights are assigned adversarially. I never assumed anything about the weights, but they're assigned up front. So this sometimes people distinguish between an online adversary and offline adversary. So this is kind of an offline adversary in the sense that the adversary has to assign the weights up front. It cannot kind of, depending on how you decide it during the course of the algorithm, it cannot then take assign different weights to what comes next in the future. So that's not possible. Good. And again, I want to highlight, the number of secretaries that will appear, the number of clients. Okay, that's the problem. So now it's kind of, you probably already guessed what the submodular version will be. So people, due to those connections to mechanism design, people get interested in the submodular version of the problem, where the objective W is not anymore a linear function, but it's a submodular function. So again, it's the definition of submodularity in terms of diminishing returns. Here, I just want to highlight that I used the notation plus E as simply union of a single element, and minus E for the same, so union E. But okay, you of course have seen that definition already a few times in this workshop, so let's not go into those details. As I said, so here as well, the submodular function is given by a value oracle that you can apply in what you've seen so far. And if F is monotone, I talk about the monotone submodular secretary problem, the monotone submodular matroid secretary problem, to be precise. So this defines the problem. So let me try to explain a little bit, give you a good, kind of an overview of what's known about the matroid secretary problem, and then about the submodular matroid secretary problem, show you a few challenges, and tell you what we try to achieve. So let's start with the matroid secretary problem, so with linear weights. So that problem is a whole bunch of results known. The best result for general matroids is a log rank approximation. So the first one was introduced by Odat, who's somewhere here in the audience. Oh yeah, far behind there. And so we have a later procedure, a somewhat simpler procedure introduced later. And then there's a whole bunch of special cases, special matrices on which constant factors, constant competitive algorithms can be obtained. So again, competitiveness is the following. So we're interested in comparing the expected value of our algorithm against the offline optimum. And we look at this ratio. It's the worst case ratio over all instances. That's the competitive ratio. Okay, so the big question is, and this is a big conjecture, but it is a constant competitive algorithm for the matrix secretary problem. And that's still wide open. So those algorithms with the log rank, I have no idea how they could be extended to constant competitive algorithms. People often call this now the matrix secretary conjecture. So somehow, so for some of those results, sometimes people assume slightly different things. Sometimes people assume that they know the matrix more explicitly. For example, maybe in a graphic matrix that you know actually the graph itself, and not just that you don't just have an independence oracle, the way I explained it. But let's not go into those details for the time being. So let's move over to the submodular version of the matrix secretary problem. So there things look much more grim. So the best algorithm for general matrix is a log rank approximation. It's a log rank competitive algorithm. And some results are known for special cases. But for the general submodular matrix secretary problem, actually the only results that are known, so it's this block in the middle, let's first focus on that, are constant competitive algorithm for for uniform and partition matrix. Then some more results are known for laminar and transversal matrix in a case where the submodular function is additionally monotone. That's the monotone submodular. I see this should be an M as MSP here. Okay, so we wondered about the following. So first, are there constant competitive algorithms for the submodular matrix secretary problem? Or is it possible that maybe this problem may be considerably harder than the linear one? So as I said, for a linear one, we still don't know a constant competitive algorithm, but people widely believe that exists. And then I would also like to understand better the relation between this monotone submodular secretary problem, the non-monotone one, and the linear one. So if the linear one is the easiest one, the monotone submodular one is the next harder one, and the submodular one is the hardest one. So could it be that one is kind of a jump in hardness somewhere in the chain of problems? And what we would like to understand better as well is we wanted to understand better if you have good algorithms for the linear version of the submodular secretary problem, of the matrix secretary problem, can you use that to obtain algorithms for the submodular version, or at least the monotone submodular version? And so we can answer with some of those questions. So our main result is we can show we have a black box reduction. So if you give me an algorithm that is alpha competitive for the matrix secretary problem on some particular class of matrix, so some fixed matrix, then I can transform this in a black box way, so not knowing anything about that algorithm, into an O alpha square competitive algorithm for the submodular matrix secretary problem. And actually, very often we can even get from an alpha to an O of alpha competitive algorithm using I've used some more insights, but that is not completely black box anymore. So the black box result is really from alpha to alpha square. And so what it means is, of course, that now the matrix secretary problem conjecture is really the same as the one for submodular functions. Because when you have a constant competitive algorithm for a linear one, you get an alpha square, which is as well constant competitive for the submodular version. So those problems are, from that point of view, they should have the same, so it shouldn't be hard. One is not harder than the other. And also what we can do is, you saw now those kind of big tables I showed to you. If you take the results from the first table about the linear matrix secretary problem, you can now just use all those results and transform them into results for a submodular matrix secretary problem. So we get a whole bunch of new constant competitive algorithms, and sometimes we can improve also on special cases where algorithms have been known previously. But I think the main, also one main thing is that we can as well get a local rank approximation now for the submodular secretary problem by essentially modifying our previous procedure we had, our previous local rank procedure for the linear matrix secretary problem. Okay, so I'd like to give a quick overview of the algorithm and a few aspects of its analysis. So it's kind of technical, the analysis, so I don't want to go into many details, but I'd like to highlight maybe one or two things that are kind of, I think is interesting to know. So the algorithm is heavily inspired by a paper of Ma et al. It's a paper that worked on the monotone submodular secretary problem for laminar and transversal matrix. And so it's more, as if a lot of main improvements in the analysis actually. But let's look at the algorithm. So the idea is the following. So we first have a learning phase. That's the first line. So first we just look at the first half of all elements without selecting anything. That's very typical for matrix secretary algorithms. And then we want to kind of construct a control set for that first half. So we run the greedy algorithm on that first half, the greedy algorithm for submodular function maximization. Again, I can be explicit here. So it's the algorithm that simply starts with the empty set, checks whether there's any element we could add to the current set without destroying a dependence, and picks the one that has highest marginal return if the return is non-negative. So as long as we can kind of add an element, I mean, it's a complicated way of saying as long as you can find an element and you can add and improve, do it. So here I have like larger or equal 0, so sometimes you may add elements without improving. It doesn't really matter. I could also have written strictly larger than 0. This doesn't make a big difference. So essentially just improve step by step as long as we can. So just to fix notation, so for me, the f e bar x is simply the marginal return of e if you add it to the set x. So it's the value of f on x plus e minus the value of f of x. So marginal returns. And so we have this control set. Now let's move on. So now we have the second half of the algorithm, new elements will appear. Now I will look at an element when it appears, and first I will check whether if this element had appeared in the first half, so in the set L, would it have been selected by the greedy algorithm? If no, I immediately discard it. If it would have been selected, which essentially this line here, if u is part of the greedy algorithm being run on k plus u, then I consider it, I will define a weight for that element, and its weight is simply the weight that, so it's W of u, which is the weight that if you look at the greedy algorithm, look at the moment when it would have added u. And then at this moment, u is a certain marginal return. And I will declare this marginal return to be the weight of that element. And then I will pass the element to the linear algorithm in a black box way. The linear algorithm may then select the element or not. That's what happens. And I simply output whatever the linear algorithm outputs to me. So that's the algorithm. So let me give you a different point of view on the same algorithm. So for the analysis purposes, it turns out to be easier to look at a different procedure, which is not even an online procedure, but it has the same output distribution. And that's all that counts. I will show that this procedure has a good competitive ratio, even though I cannot implement it that way. So I think of it as follows. Assume that, so in the previous, maybe I could go again a slide back. There was maybe one thing I kind of dropped in my explanation. There's a certain probability P. So it turns out that whenever an element could have been, so elements in the second half, I will only consider them with probability 1 minus, with probability P. With probability 1 minus P, we'll just discard them. It's kind of a random probability which are randomly discard elements. So for the time being, let's just assume that P is 1. I will come back to P, so don't get confused by P. It's not important for to explain currently. So forget about P. We'll also just delete that. So the simulated algorithm, which has the same output distribution, works as follows. So think about this set of the first half and the greedy algorithm we applied on the first half beforehand. So essentially, every element that came, so you can think of it as follows. One of three things happened to that element. Either it was part of the first half and got selected by the greedy algorithm, or it was part of the second half and got passed to the linear algorithm, or it got discarded because it cannot be, it would not have improved the first half. So think of those, I think of the set K as a set that gets selected by the greedy algorithm, and of N as the set that the linear algorithm will see. So now what I do is, let's run the greedy algorithm at the beginning. Let's assume you just run the greedy algorithm on the full ground set. You look at the element with highest marginal return. Now, but you know that only with probability 1/2 it will be in the first half. So with probability 1/2, you will put it into you will select it with the greedy algorithm, and with probability 1/2, you will just you will move it to the linear algorithm. Then you go to the next element, the next one that can be added to the greedy set. With probability 1/2, you will add it, and with probability 1/2, you will move it to the linear algorithm. So you only consider elements that can be added to the greedy set. So there's a lot of stuff that gets discarded, and so you build up two sets K and N, and A is the one that is the set of elements that gets looked at by the greedy algorithm. I guess looked at by the linear algorithm, sorry. And so I can just at the very end I call the linear algorithm with respect to the set N. It's essentially what it's the same way. It's the same algorithm. So I'll try to give you a few ideas of the analysis, but here I try not to go too much into details, and also even if you kind of couldn't completely follow the previous descriptions, I hope I can give you some insights. So first on a high level, what we have to show is, so if our control set K, I have to make sure that control set has a large submodular value that compares well against the optimal submodular value. And we can show this is the case. So it turns out that our control set is at least an 8th. It's an 8 approximation for the best submodular value so the highest submodular set in the ground set. It's kind of interesting because this is really just submodular function maximization of a non-monotone submodular function over a matroid constraint. And the interesting part is that it seems that I just used the greedy algorithm, but the greedy algorithm is not constant. It's not a constant approximation for submodular function maximization over a matroid constraint. It is a 2 approximation if the submodular function is monotone, but if not, it's not a constant factor approximation. So it turns out that the way we use it, we still get a constant factor. It's actually a very, very easy way to get a constant factor to maximize the submodular function over a matroid constraint. I will come back to that in the next slide. So let me postpone this discussion. But I first want to highlight that issue. Because we needed some algorithm that is easy to run online, to simulate online. There are, of course, algorithms known for that problem, for maximizing a non-monotone submodular function over a matroid constraint. But I don't know how I could simulate those online. So the second box on the top right, there we want to make sure that if you look at the linear weight now in the control set, that is not much larger than the linear weight you have in the set that the linear algorithm sees, right? So this is kind of this op W of N. It's just the highest weight set, highest weight independent set inside N, which are the elements that the linear algorithm sees. This is kind of important to show. Then the third box is an immediate consequence of the fact that the linear algorithm is alpha competitive. So the linear algorithm will get an alpha fraction of the best possible linear weight you can see in there. So Q, I just remind you, so Q is the set that the algorithm returns. And then finally, I have to relate that to the submodular function. So there is a last step where we use some techniques that are known in polymatroid optimization, where we use some kind of truncated submodular functions. But I want to skip that last step. I just want to talk briefly about the first box. So if you put everything together, you indeed get this 1 over alpha square approximation, so an alpha square competitive algorithm. But let's see how much time I will have left. Let's first talk about just about the first box. It's kind of a result that might be of independent interest to people, even if you don't care at all about the matrix secretary problem. So I want to explain to you how you can get an easy constant factor approximation for submodular function maximization over a matroid. And you can even completely forget the online aspect. It's really just a pure question of submodular function maximization. So what you can do is the following. Look at your ground set. First, take a random subset of the ground set that contains each element with probability precisely 0.5, and this independently with respect to the elements, and then just run the greedy algorithm on that set. And it turns out in expectation it's an 8th approximation. So that's all you have to do. So far for me, to me, I don't know of any simpler algorithm that works on a matrix constraint to get a constant factor for submodular function maximization. But again, I mean, you can get better factors than 1 over 8 if you don't need to have a simple procedure. So the key difference again is we did apply greedy, but only on a random subset containing each element with probability 1/2, and that is enough to fix the issue that greedy is not a constant factor approximation for non-monotone submodular functions. So I have time to briefly talk about the second box, which I also would like to rephrase in terms of a problem you could consider independently of the matrix secretary problem. So here again, what is the goal? I want to show that the linear weight that the linear algorithm sees is large compared to the linear weight that the control set has. So linear weight is always the weight with respect to W. I think about the following procedure. So it's kind of it looks like a different problem, but you will probably get the link once you understand that problem setting. Assume that, forget about weights for the time being. I give you a matroid, and I number the elements in any arbitrary way, let's say E1 to En. Now what I do is, I have two sets K and N, and I will go through those elements one by one. Whenever I can add an element to the set K, preserving independence, then I will, with probability 1/2, add it to K, and with probability 1/2, I will add it to N. So both sets K and N grow. So I will only consider elements that can be added to K such that K remains independent. So the only elements I consider. So of course, whenever an element gets added to K, its rank increases by 1, because I only add elements that preserve independence. This is not true when I add elements to N. Right? Then maybe it's already in the span of what you have in N. So the question is, what is the expected rank of N compared to K? And that's really, now when you think about it, that's closely related to the problem that we have, because we have a control set. And what did we do? When we later saw elements in the second half, we only added them, we only pushed them to the linear algorithm if we could have included them in if the greedy algorithm had chosen them in the first half. So essentially, we only check against the control set. And also in the future, no matter what was already sent to the greedy, to the linear algorithm, we only check against the control set. So somehow we hope that we can somehow relate what the linear algorithm sees as at least a large rank. I mean, more precisely, we hope that it has a large weight. But it turns out that if you can show that something has a large rank, very often you can use that to show that it has a large weight, because you can do some kind of prefix analysis. You can order the elements with respect to the weights, and then invoke this result for any prefix. That's a typical strategy in matrix optimization. But so it turns out, if you have that procedure, again, you can think of P equal to 1 for a time being. So now we understand P. P is really just there to, let's fix P equal to 1 still for a time being. So in that procedure, we can show that, indeed, the rank of the set N is comparable to the one of the rank of K. Turns out that it's, so if P is equal to 1, it's just an expectation half of the rank of K, at least, maybe even larger than that. It's another ingredient we had to prove. Okay, so I will wrap up here. So the main result is this black box reduction. Whenever you have an algorithm for the matrix secretary problem, you can transform it in a black box way to an algorithm for the submodular matrix secretary problem. And so in particular, if you are interested in getting constant competitive algorithms for a submodular problem, you can just focus on the linear one. That's fine. If you want to get the best constant, of course, maybe there's better things you can do then. Then you will lose something in terms of constants using our framework. But if you're just interested in qualitatively understand what you can achieve, that is enough to consider. And I think one important point is, of course, that this matrix secretary problem conjecture is still open. I think it's kind of the big question in the field of this matrix secretary problem. And now we know it's the same conjecture as the equivalent version of it for the submodular case. So I kind of strongly believe that this conjecture holds, but it's still open. Okay, many thanks.
We have 5 minutes for questions. So how general is this reduction in the sense that if you change something in the model, it still holds, let's say, the order is not random, or the constraint is not matroid, or
yeah.
It's more general than only this.
Good question. So I'm not quite sure. I mean, so with the order, so we have to watch out that we quickly get into problems where constant competitive algorithms are not possible anymore. So if the weight is adversarial and the order as well, then one can show that there's no way to get constant competitive algorithms. So there's so then also the reduction doesn't make much sense anymore. Actually, you will even get like omega of n competitive algorithms only. But maybe the other point, maybe for more general constraint sets, maybe for like matrix intersection, I don't know. Maybe it could still extend to that. We didn't really think too hard about this so far, because kind of people are really kind of focused on this matrix setting. But it's a good question. Mm-hmm. One certainly has to make sure that it's kind of we kind of broke it down into different sub-results, and has to make sure that those. I mean, the first thing would be to check whether they hold. So the greedy algorithms should still be like constant competitive, and, constant approximation.
What does the proof of greedy on a random after throwing away elements probably have? What does that look like?
It's actually pretty. It's okay. Good point. It's actually not that hard. So what I can show is that. So if you apply a greedy algorithm to let's say let's just take any ground set. Let's apply a greedy algorithm to it for a submodular function. It's not assume monotonicity for time being. So there's no randomization currently. So you can show that the set you get, it's called a set, you get Q. Fine. So the value of that set is at least half of the value of any of the set Q union any other independent set. As a result, it's already known. So essentially, you can take a union of the optimal solution, for example. So this is already enough to show that if the function had been monotone, that you have a 2 approximation. And the point is that now the problem is that for a non-monotone function, this could be worse. I mean, taking a union of sets, of course, this can be worse value. And it turns out that if I give you any set, look at any set that it's a modular value, and if I drop each element with probability 1/2, then the expected value you get is at least a constant fraction of any subset of that set. That's kind of the thing we use. It has been used in some different way in other papers. Actually, ingredients have to some extent already been there. But that's essentially with those two together, you can fix things, because one tells you that you're at least as good as some superset, and the other one can kind of break it down again on a smaller set. Yeah. Mm-hmm. Yeah, sure.
So is this true in the offline setting too, that you can, for
yeah.
non-monotone maximization, under whatever constraint, you can get a constant loss compared to what you could get for a monotone? Like using
No, there is So I mean, there is. The problem is that the first result would fail. The one that says that the value of the greedy set is at least as good as a half of the value of the union of any two of the greedy and any other feasible set. So the result uses the exchange axiom of matrix. Essentially, it creates a bijection between the greedy set, the elements there. Let's assume that both are bases, just to simplify things. So it creates a bijection between the bases and the elements of the optimal solution, so kind of the exchange bijection. And this would fail. But I think you could get it for P systems, I think, for example. Maybe the reverse constant, of course. But I think for general constraint, that would not work out. Yeah. Also, I mean, it would kind of violate some hardness results. Some of for downclosed, I'm not sure. Yeah, that's a good question. I think the way we prove it will not work At least we don't have to fix things, but at least there's no complexity theoretic reason why this would not be possible. At least I don't know of any reason for downclosed sets. For non-downclosed ones, of course, it's, yeah, there's some complexity theoretic reasons why this will not work out.